8.3 geometric sequences now. To figure out what it means to be a geometric sequence, take a look at these 4 sequences. So we're going to play that Sesame Street game where one of these 4 things is not like the other 3. Something about the patterns of getting from one number to the next is common among 3 of these and not common among the 4th. So if we look at this sequence right here, let's see how to get from one term to the next. So 5 to 15, I could add 10, but adding 10 doesn't work to get to 45. But what about if I multiply by 3, I get 15, and then if I multiply by 3 there, then I get 45, multiply by 3 again, I get 135. So let's try the multiplying pattern. If I multiply by -2, I get -2 from 1. And multiply -2 by -2, +4. By -2, you get -8. This is working. 3 times 4 would give me 12. Times 4 is 48. Times 4 is 192. 6 times 3 is 18, but then 18 times 3 is not 30. Okay, so it looks like this sequence is not following the same kind of pattern. This pattern, you multiply by something to get to the next term. Just like in the arithmetic sequences, we added something to get to the next term. Now we're multiplying by something. And that's what makes a geometric sequence a geometric sequence. And just like with arithmetic sequences, we had a common difference. That's what we were adding. We would add the common difference. Now we're multiplying by something. We're multiplying by what's called the common ratio. Okay? So first let's talk about how to find the common ratio. If I want to say, I come over here, I tell you this is a geometric sequence. When I tell you this is a geometric sequence, you know that means that I multiply by the same number to get to each successive term. So how am I going to find that common ratio? Well, if I can start at any number, multiply by the common ratio to get to the next term, then all I need to do to find the common ratio apparently is to divide this number by that number. I could also divide -8 by 4. For this one, I could divide 15 by 5, or 45 by 15, or 135 by 45. Okay? So to find the common ratio, all I have to do is take any term, call it a sub n plus 1, and divide it by the term before it. What's the term before a sub n plus 1? That's a sub n. That's how you find the common ratio. Now let's find like the equation for a geometric sequence. It's like we call it like a rule more than an equation. But anyway, to find that equation, let's take a look at this sequence. The first term is 5. Okay, so there's a sub 1. To get a sub 2, well, we're going to multiply by the common ratio, which in this case is 3. We're going to multiply this by 3. That's a sub 2. To get the next term, we're going to multiply by 3 again. We're going to multiply this number by 3. And to get to the next term, we're going to multiply by 3 again. We're going to multiply by 3 again, and so on. You can see the pattern. So, looks like we have a sub 1. For this case, we're going to do 5 times 3 to some power. Now, is it 5 times 3 to the n? We could test it. Let's see if a sub 1 is 5 then. A sub 1 equals, apparently, 5 times 3 to the n is 1 here, a sub 1. But this is 15. 5 times 3 is 15. That's the second term. So let's adjust this a little bit. Let's not make it n. We don't want 3. We actually would want 1. So if we subtract 1 from here, it's kind of offset this whole thing. So a sub 1 now would become a sub 1 equals 5 times 3 to the 0, to the 1 minus 1, which is 0. And 3 to the 0 is 1, and 5 times 1 is 5. So a sub n looks like it's the first term times the common ratio raised to the n minus 1 power. And that's exactly right. And so there you go. There's your little equation, if you like to call it that. Okay. So let's take an example of a rule that they're giving us, and we'll write the first 5 terms. Say a sub 1 is equal to 2, and r is equal to 1/3. This is number 14 in the book. Let's just write the first 5 terms. Okay, so remember, well, this is easy enough. We have the first term is given as 2, and the common ratio is 1/3. That means multiply by 1/3 to get each successive term. So multiply by 1/3, 2 by 1/3 is 2/3. Multiply 2/3 by 1/3, you get 2/9. Multiply 2/9 by 1/3, you get 2/27. Multiply 2/27 by 3, and that's going to be 81, of course. 2/81, and there's our first 5 terms. Okay, so that's just a little exercise, and again, understanding what a geometric sequence is, and just carrying that out to find the first 5 terms. Okay, and if we were given a sequence, which we've already done this, we were given a sequence, and we were able to find the formula there. Right? All we needed to know was the common ratio and the first term. Take the first term, multiply by the common ratio to the n minus 1 power, and you have it. Okay, so now that we know what a geometric sequence is, how to take the rule and write terms based on that rule, and also how to take a sequence and write a rule ourselves, now let's talk about the next step, which is the sum of a geometric series. And for this one, I'd like to get a little proofy, because, well, that's a big part of math, and it's pretty fun. So let's say we have a bunch of terms. We have a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 and so on, plus all the way to a sub n, whatever a sub n is. Okay, let's call this thing S sub n. That's the sum of the first n terms. Okay. Now let's look at these terms a little differently, because we know it's a geometric sequence. So S sub n is a sub 1. Okay, so a sub 1 is a sub 1. But how do we get a sub 2? We take a sub 1 and we multiply it by the common ratio. Okay. And how do we get a sub 3? Well, we take a sub 2 and we multiply it by the common ratio. But a sub 2 is just a sub 1. Sorry, that should be a sub 1. It's just a sub 1 times r. So we'll take a sub 1 times r and multiply it by r, which would be r squared. And then we'll do this one more time. How do we find a sub 3? Well, we take a sub 4. We take a sub 3 and multiply it by r, but this comes all the way back from a sub 1. So we just take this guy and multiply it by r again, which is r to the 4th. To the 3rd, I apologize, the 3rd. Okay, all the way up to a sub n, which is going to be a sub 1 times r to some power. Let's look at the pattern we've got going on here. A sub 2 is times r to the 1st, 2, 1. A sub 3 is a sub 1 times r squared, 3 to 2. So, and then a sub 4, r is raised to the 3rd power. So at a sub n, we're going to have a sub 1 times r, not to the n, but to 1 less than n, so n minus 1. Alright? So to kind of prove the formula, or the equation for this sum of all these terms, I'm going to do something that's not obvious. It's a little tricky, but it ends up being pretty neat, I think. So I'm going to multiply both sides of the equation by r, the common ratio. So multiply r times S sub n, and that's going to be equal to, I'm going to multiply all of this by r, which means I need to distribute r. Okay? So that's going to be a sub 1 times r plus a sub 1 times r squared plus a sub 1 times r to the 3rd, and so on, all the way down to a sub 1 times r to just r to the n. Okay? What's before this? What's going to be right before this term? Well, it's going to be a sub 1 times r to the, not the n, but 1 less than n, so n minus 1. Okay, so you can see if I look kind of diagonally, there's this a sub 1 times r, and a sub 1 times r, and r squared, and r to the third, and you can see that's going to match up all the way down to n minus 1, and then r to the n, a sub 1 times r to the n is not going to have a partner. Also, a sub 1 by itself, it doesn't have a little partner at all. Okay, you can see that this matches up with that, and so on. But this guy, this guy's left alone, and this guy's left alone. Okay, so that's just something I want you to notice right off there. So the next little part of the trick is I'm going to take s sub n and subtract s sub n times r. Let's put the r right there. All right, I'm taking this and I'm subtracting this minus this. Well, if I do that, if I subtract r times s sub n from s sub n, then on the other side of the equation, I could take this big long expression right here and subtract this big long expression here. Well, when I do that, I'm going to get this minus this. They're going to cancel each other out. This minus this, they're going to cancel each other out all the way down the line with all of these pairings getting canceled out. And then I'm going to still subtract this last term. So I'm going to have this didn't get canceled out, so a sub 1 minus, all of these are getting canceled out, and then this is left on the end, minus a sub 1 times r to the n. Okay, now I'm going to do some factoring. These kind of a common factor of s sub n, so I'm going to factor that out. S sub n times 1 minus r is equal to, now these have a common factor of a sub 1, and that's going to leave r minus r to the 1 minus r to the n. Now remember, s sub n, that was the thing we were looking for to begin with. That was our original problem. How do we find this sum? Well, there it is. It's still there. There's the sum, s sub n. So all I need to do to get s sub n by itself is divide by 1 minus r. S sub n is equal to a sub 1 times 1 minus r to the n over 1 minus r. Okay, so there it is. There's the formula. If I want to know how to find the sum of the first n terms of a geometric sequence, then all I need to do is take the first term, multiply it by this fraction here, where the numerator is 1 minus r to the n, the common ratio to the n power over 1 minus r. Okay? We've got just enough time to think about the sum of an infinite geometric series. The cool thing about geometric series is that you can add up an infinite number of them, provided that one thing is true, that the absolute value of r is less than 1. Okay, so whether r is positive or negative, just take the absolute value, and it needs to be less than 1. Okay, so you can think of it as like a fraction between 0 and 1. So if this is a fraction that's between 0 and 1, think about what happens to this equation here as n gets rather large, because n is the number of terms, and if we say n is infinity, we're saying, well, what happens when I add up an infinite number of these terms? Well, let's take a look. Think about, let me rewrite this up here, minus r to the n, something less than 1 to the n. Let's take an example of 1 half. 1 half times 1 half times 1 half times 1 half, like a bunch of times, an infinite number of times. Well, what's going to happen to this? Let's represent the infinityness of this by putting those dotted lines, or dots right there. What happens when we multiply all these 1 halves together? We're going to get 1 over this huge number. This is kind of improper to write this, but this huge number, what happens when you take 1 and divide it by a huge number? You take one thing and divide it into a billion, jillion, quadrillion, whatever, pieces, googolplex of pieces. Each of those pieces is going to be very tiny. It's going to be pretty much 0. Okay? So pretty much 0 is just right there. Just goes away, becomes just insignificantly small. So what we're left with is a sub 1 over 1 minus r. So that's the sum of an infinite number of terms of a geometric series where r, the absolute value of r, is less than 1. I'll see you in the practice videos.